In this series of lectures, we introduce some basic and important concepts in calculus. As an entry-level course, we often adopt approaches that are intuitively clear, but might not be mathematically rigorous. In particular, we will not use the famous epsilon delta language. In this lecture, we'll look at something called L'Hopital's rule. Okay, there are different scenarios to apply the L'Hopital's rule. Here, we just focus on the so-called 0/0 type. All right, let's look at an example to demonstrate what is the 0/0 type. Okay, so suppose we want to find the limit, which is 1 minus cosine x over x squared as x goes 0. Now, if we try to plug the x equals 0 into the numerator, right? So, okay, we say, all right, so I let x equals 0, so this will be 1 minus cosine 0, that's 1 minus 1, which is 0. All right, now how about the denominator? The denominator is 0 squared, which is also 0. Okay, so here the point is we end up with something which is 0/0, but we don't know what is 0/0, right? And this is called indeterminate. There are several different forms of indeterminate forms. This is one of them, 0/0. Okay, so that's what we will focus on. Now the question is, how should we handle this kind of indeterminate form? And that's what L'Hopital's rule tells us. All right, so here are the statements of L'Hopital's rule. It says this. All right, so suppose we want to find the limit of function fx over gx, right? Just like right here. This will be, so here, this will be my fx, right? So this will be my gx. Now, I want to find the limit as x approach to a point x0. Now, what we have is fx0 and gx0, they are both 0. So we cannot just plug into the function because that will end up with 0/0, which is indeterminate, right? All right. Okay, so if we further assume that the derivative of g does not vanish, it's not 0 when x is not 0, and then the L'Hopital's rule tells us the limit of fx over gx is the same as the limit of the quotient of their derivative. So they're the same if we know the limit of the right-hand side exists. Now, in particular, if we further have that the derivative of g at the point x0 is not equal to 0, then we just have a quick answer. The limit is the quotient between their derivatives and the point x0. Okay, so this is the L'Hopital's rule. It has transformed the limit of the quotient to the limit of quotient of their derivatives. Okay. Let's look at, let's say this is, I called the general case, which is 1, and this is special case, which is 2. Let's first verify special case 2, which is very easy to check why it's correct. Okay, so what we can do is, I can write, all right, so let's look at this case, what's correct, right? So we assume the derivative of g at a point 0 is not 0. Okay, so then I can rewrite fx over gx equals fx minus fx0 over gx minus gx0. Now, why? Because remember, this is 0 and this is 0. All right, so if I subtract the 0, it doesn't really matter, right? Okay, and then, but this is still, you say, oh, this is still not so clear. Okay, so if I can do one more step, so this is fx minus 0 and divided by x minus 0, right? Then because here I've actually this one, I have to multiply back. So this is gx minus gx0, right? Okay, now let's see. Here I have two things. This is one thing, right? So this is one thing, and there's another thing, right? Okay, so it's this one. Okay, now we want to send, well, what do we want? So we want to send the x goes to x0. Now you look at this, what's the limit as x goes to x0? This is exactly the derivative, right? By definition, this one, as x goes to x0, this one just goes to the derivative of f at a point 0. This is by definition. Then how about this? It's okay. How about this term? Well, this I can just write as 1 over, right? So, okay, so this is just 1 over. This is gx minus gx0 and x minus x0, right? Now, what is this one? Again, by definition, as x goes to x0, this one just goes to the derivative of g at the point x0. All right, so eventually you just end up with L prime x0 over g prime x0 as x approaches 0. So my point is, for this special case, it's very easy to establish. You just by a simple algebra plus definitional derivative, and we just get the limit of the left and right are the same. All right, now let's look at a more general case, right? So for this case means we don't really know. It could happen. The derivative, right? For this case means in general, the derivative at this point could be 0, right? And then what we say is we just look at the limit instead of just plugging 2. All right, so let's look at this case. Y is correct. All right, so let's look at the proof. Okay, so here I look at, right, so this is what we have. I look at the point. This is x0, and then I look at this is x0 plus h, right? So we look at the interval of this. And I design a function hx, which is f evaluate these endpoints times gx minus g evaluate this endpoint and times fx. All right. Okay, let's see. What can we say about the function? Of course, the function is continuous, differentiable. More importantly, let's see what is the value of this function at endpoint. So what's the hx0? Okay, so this is just x0 plus the h and gx0 minus this gx0 plus h and fx0. Okay, but what do we know? Remember, we know that the value of f at g and g at the point x0, they are both 0. Okay, so we know this is 0, this is 0. So okay, so it's 0. And then how about the value at the right endpoint, right? So this is okay, we just plug into. So this is x0 plus h and gx0 plus h minus gx0 plus h times the fx0 plus h. What's this? Okay, you find they are exactly the same. So this is also 0. Now you see, we have a function, right? So it's okay. Now we have a function with h, which is 0 here, and also 0 here, right? So this is a function, y equals hx. It's both 0, right? So if we try to use the coordinate, so 0, this is x, and this is y. And okay, so now we can use the mean value property. We say, all right, so now by the mean value theorem, right? By the mean value theorem, we say, okay, if these two endpoints are the same, that this is special case of the mean value theorem, right? So then there's the point which we say we like C, and the derivative is 0, right? So the derivative of this one is 0. Okay. And by there exists C, which is between x0 and x0 plus h, such that the derivative of this C, which is 0. But what is this? Well, this just implies the fx0 plus h times g prime C, and then minus gx0 plus h. This is the f prime C. This equals 0. Okay, so we can rewrite this. This just tells us, right? Okay, so if I rewrite this, just tells us the g. Hold on. So this just tells us the fx0 plus h over the gx plus h. This is the same as the L prime C and G prime C. Now, you say, okay, I want to send the h equals 0. Just means this one goes to x0 and this one goes to x0. Then this one will also goes to x0. This also goes to x0, right? So we say, okay, so then this gives us, from here we say, all right, we just got what we want. If I have the x goes to x0, the fx over gx will be the same, given the right-hand side exists, right? So L prime x over g prime x. Suppose the limit of this one exists, right? Okay, so this is how we prove the L'Hopital's rule using the mean value theorem. Okay, all right. Okay, so now let's see the application. So first of all, let's look at the example 1. Here we want to find the limit as x goes 0 of 3x minus 3x xc over x. So this is 0 over 0, right? Because when x equals 0, this one equals 3 to 0, minus 2 to the 0, which is 1 minus 1, that's 0. And this is also 0. So this is 0 over 0. Okay, so let's apply the L'Hopital's rule, right? All right, so then we have the limit. Let's use this L'Hopital's rule. All right, so it's okay. So this goes 0, 3x minus 2x over x equals the limit. X goes 0. Let's take the derivative. So this is my fx, and this is my gx. Okay. All right. So that's you take the derivative. This will be 3x log 3 minus 2x log 2 and over 1, right? Because we have the derivative of this is 3x log 3 minus 2x log 2, and g prime x is just equals 1, right? Okay, so now you see this is good because it's just 1, right? And goes to 0, so we get okay. So this one will just goes to this will just goes to 1, and this also goes to 1. So eventually you get this log 3 minus log 2, right? Okay, so here's simple example that we can apply the L'Hopital's rule. Now let's go back to the first example we mentioned. Right? So limit 1 minus cosine x over x squared. Okay, so what do we have here? This is my fx, right? This is my gx. It's 0 over 0. Okay. Well, so we use the L'Hopital's rule. So this is equals the limit. Okay, so we use L'Hopital's rule. Okay, so this is the limit as x goes 0. Now I take a derivative. So this will be g at 2x, right? Take the derivative of this one, take the derivative of that. And here will be sine x. Okay, so you just get this 1/2 the limit x goes 0 over sine x. Now remember, the limit of sine x over x, this will just be 1. This is what we showed before. It's 1. And which is just the derivative of sine. Also, this is just the derivative of sine x and x0, right? Okay, all right. This is what we have. Now, some of you might want to say, we can use the L'Hopital's rule to do this, to get the sine x over x. But if you use the L'Hopital's rule, there's a logical problem, because if you use the L'Hopital's rule, then you have to look at the derivative of sine x. But remember, in the previous lecture, the way we derive the derivative of sine x and cosine x is we use the fact that the limit of this one equals 1. So that means you have a logic loop if you try to use the L'Hopital's rule to get sine x over x. But anyway, so here's what we have. Okay, example 3. Let's find the limit. 1 over log x minus x over x minus 1. Here the point is, if x go to 1, you see this is like infinity, this guy infinity, so you can infinity minus infinity, it's indeterminate. So what we do is, let's first combine this, right? So okay, we have log x minus 1 over x minus 1. So this will be, I just combine these two fractions. So this is x minus 1. Maybe I'll rewrite the other way, right? Okay, this is the log x, right? And then this will be x minus 1 and minus log x. Now, obviously, this is 0 over 0 type. If you plug x into the quotient, both the numerator and denominator is 0. So this is 0 over 0. All right, so then we can apply the L'Hopital's rule. So we get the limit. If you try to find the limit as x goes to 1, the limit as x goes to 1 will be equals the limit as x goes to 1. We use, let's find the derivative, right? So remember, the derivative of this one is 1 over x. So so 1 over x is the derivative for a log function. And now let's find what's the derivative of this. This is product, so we can use the product rule, and you find this is log x and plus x minus 1 over x, right? Okay, so then the derivative of the numerator is kind of easy to find. So this is 1 over 1 minus x, and then this will be x and a plus 1 minus 1 over x, right? Okay, now you see this still, but the point is, if you plug x, you can find this still 0 over 0 type, right? If you plug x1 into here. Okay, so then we have to simplify this one. So okay, let's simplify this. So x minus 1, right? Okay. Okay, so here's the place we use the L'Hopital's rule. L'Hopital's rule, right? Okay, so here we use algebra. We multiply x on both sides. So this is x minus 1. This is x log x and plus x minus 1. All right. Now, again, this is 0, 0 over 0, right? So we use the L'Hopital rule again. So it's okay. Let's use the, one more time. Let's use the L'Hopital's rule one more time. And then this equals the limit as x goes to 1. You take the derivative of this is just 1, right? So the derivative of this x minus 1 is just 1. And derivative of this, right, is okay. We just use, this is against the product rule. You'll get this. Okay, so this is just log x and plus 1. And this is plus 1, right? All right, so now everything's good. Because if you let x equal to 1, this one just goes to 0. Okay, eventually we end up is 1/2. So the answer is 1/2. Here, the point is that we need to use the L'Hopital rule twice, okay, in order to get the final limit. Okay, let's look at question problem number 4. Let's say we want to find the limit of this guy. Again, clearly, this is 0 over 0 type, right? If you plug x into the equation, you get this is 1, this is, if you let x to 0, right? You say, okay, if you let x to 0, so this will be 1, minus 2, sine 0, but sine 0 is 0. Okay, so 0, so okay, you see, this is 0 over 0 type. All right, so then we are at the perfect situation to apply the L'Hopital's rule, right? So, okay, we say, all right, let's apply the L'Hopital's rule. By L'Hopital's rule, we know this equals the limit as x0. Let's take the derivative. The denominator is 3x squared, right? So if you take the x cubed, take the derivative 3x squared. And then you take the ex, the derivative of ex is the derivative of ex, just ex, right? So the derivative of e negative x, this is negative e negative x. Okay, so by the chain rule, right? So we then get this e minus x and then minus 2 times cosine x. Because remember the derivative of sine x, this is cosine x. Okay, it's cosine x. Now let's examine this. Are we done? Not yet, because if you if you let x equal 0, you'll find this is 1, this is 1, this is minus 2, and this is 0. Again, this is still 0 over 0, right? So this is still over 0, 0. So what does that mean? That means we have to apply the L'Hopital's rule again, right? So you say, okay, let's apply. So we say, all right, so let's apply the L'Hopital's rule again. So let's apply one more time. Rule. Okay, so then this will be the limit as x goes 0. This will be 6x, which is derivative of 3x squared, right? And then we have ex and minus e negative x. And then this plus 2 sine x. Because remember the derivative of cosine x, this is negative sine x. Okay. All right. Okay, so what do we have? That's what we have. Are we done? Not quite. Because if you let x go 0, you get this is 1 minus 1 plus 0. This is 0, still 0 over 0. It's okay. Still is 0 over 0. Okay, still 0 over 0. It's all right. Okay, so what should we do? Just one more time. So apply the L'Hopital's rule one more time. Go one more time. And then we say, okay, so this will equals the limit as x goes 0. Now I take the derivative. This will be 6. And this is ex and plus e minus x and a plus 2 cosine x, right? Now, everything is fine. Because if you plug into 0, you say, okay, if I let x 0, okay, so this one just go to 1. This will be 1, and this will be 2. This will be 2 because cosine 0 is 1. Okay, so then you end up with 4 over 6. That's 2 over 3. We are done.